Let's resume. So one of the most important concepts in analysis is the concept of a continuous function. Okay, so this is one of the central concepts of this class. We now have the machinery to define what we mean by a function to be continuous. So first of all, let's build some intuition. What do you mean by function is continuous? So if I draw the graph of a function, what would you say is true about a continuous function? Is this function continuous? Where it's defined anyways? Would you say this function is continuous? Everybody? Yes? Well, what do you mean? What do you mean by that? Would you say this function is continuous where it's defined? 2 points. It's defined on 2 points. That's that there, and that's that there. Would you say this function is continuous where it's defined? How many people say yes? How many people say no? Okay, everybody form an opinion. Is this function continuous where it's defined? How many people say yes? How many people say no? If there's several of you who didn't vote. I want everybody to form an opinion. It's okay. It's okay. Get it. I don't expect you to necessarily see this right away. Should this function be called continuous? How many people say yes? How many people say no? Ooh, some of you changed each other's minds here. Interesting. Okay, we'll come back to that. Why is this function? Why would you say? Okay, why would you say this function is not continuous? You probably would say this function is not continuous. This is a graph of a function that's not continuous. Willie.
Because if we call that point where there's a complete, so we say the limit of f of x as x approaches p is not equal to f of p.
Oh, interesting. So would you agree the issue here is that as x goes to p, f of x looks like this, but f of p is right here, yes? Would you say this function is not continuous? Even this one's not continuous. This limit exists, but if at p this point is defined differently, we also have the same problem. Right? Here these points, as you approach from left and right, converge to something, but it's not f of p, yes? That's the definition. This is good. Is this continuous? Interesting. But this one is. You're okay with this, right? So really, what does it mean for a function to be continuous? It means the function value at every point is exactly what its limits suggest. Okay? That's the intuitive way to think about it. So let's make a definition here. Definition. As before, x and y are going to be metric spaces. Now, we're going to consider some subset of x that the function is defined in. But this time, I want you to notice, we're going to demand that p be an element of this subset. Okay? And we're going to assume we have a function that goes from e to y as before. Okay? But p is going to live in e. Okay. We're going to say the function is continuous at p if, what I mean by it means the following. For every epsilon bigger than 0, there exists a delta bigger than 0 such that for all x and e, help. I want to say the limit is what you think it is. That is, I want to say, another way of saying this is the limit of f of x is f of p. So what would change in this definition? Not much. but for every epsilon there's delta such that, yes, David?
Change Q to F of P.
Okay, good. Change Q to F of P and? Well, no, we're going to keep delta bigger than 0, but we just won't exclude 0. We will allow x to be p. That's okay too. Because after all, if you pick x equal to p, you'll have f of p and f of p, their distance is 0. That's okay. So we remove that restriction such that dxp less than delta implies the distance of f of x and f of p is less than epsilon. Another formula, another definition you should memorize, commit to memory. This means the following. F is continuous at P. Okay, so no restrictions anymore. X may be P. The other thing here is P is an element of E. P is in E. Okay, I just said that. P is in E. Just want you to notice that. It's in fact an E factorial. Kidding. Notice that this is saying that the limit is f of q, right? So really, we're saying, in fact, just what our intuition is. We're really saying, well, I'll just say this was p, right? Q is f of p. Okay, that arrow just means look. Notice that. So really, here's the theorem, which follows just by definition now. If P is a limit point of E, then F continuous at P means, this is equivalent to the limit as x goes to P of f of x equals f of P. Okay? They're exactly the same thing, as long as P is a limit point. The other thing I want you to notice is, again, so this also follows. Also, check this out. Here's really what we're saying. Suppose I look at the sequence characterization. What I'm saying is if you take a sequence converging to P, then the limit of f of the sequence is f of the limit of the sequence. So if xn converges to P, if xn is a convergent sequence, let's just say that. Well, then f continuous is equivalent to saying the limit as n goes to infinity of f of xn is f of the limit as n goes to infinity of xn. In other words, for continuous functions, you can switch functions and continuous functions and limits. It doesn't matter which order